Welcome to another exciting microcontrollers class. In our last exciting microcontrollers lab, we were doing work with the I2C bus using the real-time controller chip known as the Dallas Semiconductor 1302. And I thought what would make sense is if we could have a little discussion about the I2C bus. This is called a two-wire bus, and you can kind of see that outlined here in this little Fritzing proto board. We've got a little temperature sensor here, and we've got some power and ground being distributed, and the temperature sensor is coming in on for the Arduino Uno, industry standard de facto lines 4 and 5, which basically means that you've lost two analog inputs. And so what happens there is, you've got to take into account the fact that you've lost analog channels 4 and 5. And if you needed them, well, this may not be the right bus for you, or you'll have to change the allocation somewhat in the software. But in any case, this is just as though we had SPI coming in on lines 9, 10, 11, 12, and 13. Here we have I2C coming in on bus lines 4 and 5. So as a result, we've got ourselves a new bus, but it's only 2 wires if you exclude power and ground. And it's got a couple of 47 kilo ohm resistors being used as a pull-up. And so we've got an opportunity now to add lots and lots of extra peripherals, provided we don't saturate the bus. And so the bus has got limits, but on the other hand, a 2-wire bus is a very convenient bus. And so I thought it would make sense for us to discuss it a little bit. Let me see if I can get this to go full screen. Oh, there we go. That worked out. So here's what I'll do is I'll intersperse example chips that you can get in the I2C bus. And you say, well, what's it used for? And what's really cool about it is you only need a serial data line and a serial clock. That's SDA and SCL. And the rest of the stuff, power and ground, maybe this little guy here has an alert. Not every chip has it, but a chip manufacturer can standardize on the I2C bus protocol, and you'll find a lot of chips are available. This one is an analog devices A to D converter, rather precise, and also available on the I2C bus. And, you got a trade-off now. If you want to add some more wires and go full duplex, you can with SPI. But with I2C, you can go a little bit further, a little bit slower, and a little fewer wires. So that's kind of nice. And so what I thought I'd do is run you through some examples so you could see what's going on here with this I2C bus, and maybe examine some of the trade-offs so you know when it is appropriate to use it and when it is not, because it's not the best thing for high-speed stuff. So here's a little Eagle schematic. This one has an I2C master, which would probably be your Arduino Uno. Although it is the case that you can have one Arduino Uno talk to another on this bus. So your slave can take over. These are the pull-up resistors, R1 and R2. 47 k ohms is normal. You don't want to have a pull-up resistor on every device. You only want one pull-up resistor for the bus. And, some people say, well, what do I need a pull-up resistor for? What's that about? And the answer is, if you were to shout into a room like an auditorium that didn't have any people in it, you'd hear an echo back, right? That echo back is normal, and you're used to it, and you just know that it's an echo. But the electronics from the data bus, they don't know that it's an echo. So they'll send out a command. If it echoes back, well, that's a problem, because they're going to see that as additional data, and it'll get confusing to the chip. So what you want to do is suppress that echo. That's what these resistors are doing. These long wires, these twisted pair wires, have essentially what's known as parasitic capacitance. So that they'll end up taking in a charge and then bouncing that charge right back at you. And so just like in an auditorium, if you want to do something to suppress the echo, You add sound suppression materials like sonics or curtains or cushy chairs or people, anything to absorb that echo because it's too annoying to have a lot of echo. So 2 wires, got to, it's a bus, but you got to treat it like a transmission line, which means you need your termination resistors. And you'll see this in other buses too. The ancient SCSI buses always had termination resistors on them. And you don't need multiple termination resistors because that causes what's known as double termination. And if you keep adding termination resistors, you're actually lowering the overall resistance because you're hooking those resistors up in parallel. So that's not good. So you really just need one set of resistors and presumably at the end of the bus. So you terminate at the end and just once. And lots of other things you can interface to. Timers, real-time timers. You can interface to temperature controllers, LCD devices, double EEPROMs, other microcontrollers. As long as you can, I guess, stand the fact that it's not the world's fastest bus, it's very convenient. Here's a typical sort of I2C interface spec that you might see in the data sheet, right? So what this is doing is it's giving you address options. When a bus like this, in comparison to SPI, which has a chip select or a chip enable, you don't have that. What you get is an address. So you have to address the devices in the bus. And a lot of times the devices will come with a fixed address or a fixed set of addresses. In this case, we have a little serial digital thermal sensor. These thermal sensors are really good for I2C buses because I2C buses aren't that fast. And so slow things like temperature, that's just fine for an I2C bus. It's 2 directions, but not at the same time. So that means it's half duplex. And what you can do is you can run these things up at speed, 100 kilobits per second. Arduino's got no problem with that. 400 kilobits per second, Arduino can do it fast mode. Fast mode plus, they call it. That's a megabit per second. So you're getting up there now. And then 3.4 megabit per second in high speed mode. I haven't tried our Arduino Unos in high speed mode, but if all you want to do is get the temperature, you really don't need it. So data transfers between the ICs, we call them low rate because comparisons, right? Let's compare it. I2C versus SPI. Yeah, I can go 3.4 megabits per second in high speed mode, but look at SPI. That can run 60 megabits per second. So if you want some RAM, nice high speed RAM, then you don't want I2C. You just don't. And when you look at the chip that I added, the MCP 4921, which is the 12-bit DAC that you guys have been playing around with in the Audio Shield, that was an SPI DAC, a high-performance DAC. And you were able to sample at very high speeds. If you wanted to add some RAM, probably want to add it onto the SPI bus. Now, here's an example of a chip which costs about 85 cents retail. I just priced it this morning. It's a megabit of ultra low power serial RAM, static RAM. Has a standard SPI interface, and it has a clock frequency of 20 megahertz. Now, having said that, your Arduino Uno only goes to 16 megahertz, and probably you're going to divide by 2 to run it on the SPI bus, so you're probably only going to run the RAM at 8 megahertz, but you're not going to find 8 megahertz SPI RAM because that's just slow. So if you want to run something like an 8 megahertz bus, you really don't want I2C. That's not the thing. On the other hand, if you said, you know what, I can handle the fact that we're going to digitize slower and I don't mind not having like full bandwidth audio, then yeah, you can run I2C RAM. You can even find I2C double EEPROM, and we'll see that a little bit later on. Also, you can find I2C DACs, I2C A to D converters, no problem. But the common stuff, high-speed serial RAM, you're going to want to go to SPI if you care about speed. Now, one thing you could do is you could balance the two. You could have like an I2C bus enabled ADD converter and a I2C bus enabled DAC, and then throw on an SPI RAM. And that might make sense because you're reading and writing from the RAM like twice as fast as you're reading and writing from the ADD converter and the DAC, especially since you're only sampling at, let's say, audio rates for the input and the output. But when you want to do your digital signal processing, you want to go at full CPU rates. And so for that reason, you'd want to have a higher speed RAM. But even so, serial RAM is not going to be as fast as parallel RAM or the RAM which is internal to your Arduino Uno. But having said that, if you're adding all of this stuff, right, A to D converter, D to A converter, extra RAM, and you're adding it to an Arduino Uno, you might want to consider getting a better chip. Like you could get the AT Mega, right? If you get the Mega, it comes with a built-in DAC, built-in A to D converter, and more RAM. So if it's already in the chip, at the end of the day, when you price it at the margin, cost of a shield plus fabrication plus assembly plus the chips that go on it, you're better off with a better chip. And you're going to have things run a lot better. I mean, all around, it'll be cheaper, it'll run better, have more features, all that other stuff. So think of it holistically, think of the whole system, and think carefully before you start adding chips to your Arduino Uno, especially if you can find those features already available in the next higher up chip. Because after all, Arduino Uno is just an 8-bit toaster controller, and the Mega is a 32-bit machine. So that's kind of a big difference. And it's not all that much more expensive. It really isn't. So then let's look at some of these I2C bus characteristics. We already mentioned it's a 2-wire. It's got the clock. It's got the data. It has a start-stop condition. And it has a protocol, which is really rather important because what happens is you've got acknowledgments, you've got addresses, you've got commands, you've got data. You have all these different interesting and wonderful bits that have to be packed. And when you're doing this, you use a special library called the wire library. And whenever anybody builds a driver for a chip, they start with the wire library. Just like if you were going to build a driver for an SPI-based chip, you might start with the SPI library. So the wire library refers to the 2-wire interface that you'll find when you wire up your new chip. And they call it an integrated circuit. IIC. And so you get a lot of these manufacturers who will embrace that interface because it's so common. It's a de facto industry standard devised by Philips some years ago. And so we have like little LCD displays that use it, temperature sensors, compass sensors, touch sensors. You can basically shop around for a whole bunch of stuff that comes with the I2C interface, and that's cool. In fact, if you wanted to, you could go to like DigiKey, look for ADD converters, and just sort on those that have I2C interfaces, or look for DACs that just have I2C interfaces, and you'll find a bunch of them. Here's that little temperature controller again, and you can see what's going on here. He's got data bits which are being allocated, and they're giving you commands for the temperature controller. And the only way you're going to learn how to write a driver for a new chip like this would be read the data sheet. I think that's the most important thing. And the other issue is you're going to have 400 picofarads of parasitic capacitance on one of these I2C buses at most, but that's a lot. You know, typically I have ribbon cable that gives me 11 picofarads of parasitic capacitance per foot, which is a lot. You know, 1 foot later, you can't run things faster than 450 nanoseconds because that capacitance looks like a big low-pass filter, and it takes those square waves and just rounds them out. So that's what happens when you have parasitic capacitance. You're basically dealing with a low-pass filter. And so if you want to run this thing high speed, 12 feet's kind of a lot, actually. That's a big bus. I mean, you could put a lot of stuff out on 12 feet worth of bus. So that's kind of nice. I don't think you can do that with SPI, especially in its high speed state. So you got to know something about what's going on with the clocks. You have to know what's going to happen with the signals. And here comes a little example code. And you see how it starts. He includes the wire.h, and then he has to have an address for the temperature sensor, which probably came right out of the data sheet. And he wrote it as a decimal number, but he could just as easily have written it as a binary number, preceding it with a B. And that's quite typical. Right? So here comes the setup. We're going to start with the serial.begin 9600 baud, and we do a wire.begin. So you know serial.begin, if you're in the wire interface for two-wire protocol for I2C, you got to do a wire.begin. That sets things up in the setup. Here's an example of an I2C compatible or ISPI capable chip. And this one is a 24-bit, 192 kilohertz. This is called a Delta Sigma analog to digital or digital to analog converter. This is quite common, actually. You can see these in consumer electronics devices. 192 kilohertz refers to a 1-bit A/D converter that's essentially acting as a successive approximation converter. It's doing a kind of slope integration, which is beyond the scope of what I'm going to lecture to today. But in fact, you can get chips that do this. They sit on the SPI or I2C interface, and 24 bits. That's 6 dB per bit. Actually, 6.02 plus and then some. So probably something on the order of 24 times 6 is 144 dB. I doubt you're going to get there. Probably going to stop at about 120 dB, if that, because you're going to have thermal noise. You're going to have noise from your chip, your Arduino. You'll have all kinds of interesting digital noise around, but you know what? If you can get to 100 to 120 dB signal to noise ratio, that's great. That's really great. Here's a blow up of the schematic for a I2C. You've got your pull up resistors, R sub P, over in here, and you need them for the data line and the clock line. And then you have your high impedance capable outputs, right? So what you can do is you can turn those on or off depending upon whether you want the serial clock to be asserted or not. And so that gives you the ability to go to what's known as a tri-state system. And this is being diagrammed out as a field effect transistor. And so that's the gate. And so now you've got a way to just keep glomming on one device after another. And when the device is not being addressed, it will not assert its output on the data line. So it will basically not speak until spoken to, put it that way. So here's another example, wire.begin transmission. Here comes the address. We're going to write a 0, end the transmission, and we want to request the result, the temperature. So we go to an address that we've written out. We say we want the result, and we wait for the wire. Wait for it to come back, and when it does, we just do a wire read, and that gives me the temperature. And that's it. That's how you read a temperature sensor. Here's the 24-bit A/D converter. I keep throwing in these chips because you got to see there's a lot of chips available. This one is from Microchip. They're the same guys who made the DAC that we were using, and it says it's got both SPI and 2-wire because they know people sometimes like both or either. And so he's got 107 dB, which, I didn't think you were going to get 6 dB per bit, but 107, well, he says total harmonic distortion. Then 112 dB spurious-free dynamic range. I suppose he's thinking after 112 dB, you're going to get something spurious. I don't know what. But in any case, what's the point of having 24 bits if you only get 112 dB, right? I mean, if I think about it a different way, if I had a 20-bit DAC I probably would get close to 120 dB in theory. And this thing is, well, probably running closer to a 19-bit DAC. 19-bit DAC would give me perhaps 114 dB. So I don't know. Seems like he's wasting a whole bunch of bits there, but what are you going to do? Here's a couple of ways you can look at the I2C. This is not quite a token ring because we're not connected over in here, but we got a gate array, microcontroller, LCD driver, some double EEPROM or RAM, another microcontroller. They can all take turns chit-chatting with one another. I don't know what they're talking about. Perhaps the ADD converter says, here, microcontroller B, here's some data. And it says, okay, I'm going to chew on this for a while. And then presumably uses the gate array for some kind of signal processing, the LCD for display. Perhaps it's doing spectrum analysis. And it needs the RAM to store stuff, or the double EEPROM. And microcontroller A, I don't know, maybe he drives the LCD driver. Not quite sure what these all are doing. This is just thrown together. Here's what happens if you're going through a SPI bus. Now I've got a daisy chain, the serial clock, the MOSI, and the MISO, and I've got to have a separate serial select for every single chip. So if I have 13 chips, I got to have 13 wires for serial select, which I could probably get out of a decoder, maybe a 4 to 16 decoder. But then I'd also have to wire in the MOSI, the MISO, and the serial clock. So it's a lot of extra wires. Plus, then there's also this distance issue. You know, maybe you can't really go 12 feet with an SPI. That's a problem. Maybe you want to go further. So in that case, SPI might not be right for you. So I want to connect to clock. I'm using the standard Arduino pins 4 and 5. If I'm on the Mega, the standard pins change to 20 and 21. And you know what'll happen is they'll have some sort of a dispatch in the macros, and it'll say if it's an Uno, these will be your input pins. Whoops. If it's a Mega, those will be your input pins and output pins. And this is the typical block diagram for the topology. Device N. So having a bus is cool. Here's a another example of an I2C device. This one is kind of neat, actually. I just found this one today. It's static RAM, and it's double EEPROM. So when you write to the static RAM, it goes fast because it acts like static RAM, but it also backs up on command to the double EEPROM that it contains. And it's good for 100 years. And I'm like, whoa, how do they know that? Because this company's not 100 years old. And they didn't have it 100 years ago, because 100 years ago, everybody had tubes, right? They didn't have this. So that's kind of neat. And he says he can run this out to a standard 1 megahertz line. So that's nice and fast. And so it says here I can do 127 different devices because I got 7 bits worth of address, which is, I don't know. I maybe I have a problem with my imagination, but I just can't imagine putting 127 different devices on my Arduino Uno. That just makes my whole head explode. It goes, 127 devices on an Uno? What are we doing? So probably that won't happen. And if you had 127 different devices on the Uno, what would they be doing? Like if they were all measuring temperature, that would be okay. But if they were all static RAM, you wouldn't be able to keep up because they would clog, you know, you'd be IO bound. They'd clog the network just the way I-95 gets clogged when there's a traffic jam. You know, it wouldn't work from a system point of view. So then here comes a little timing diagram. I don't think you guys get too much in the way of timing diagrams, so it doesn't hurt to show you one. You want the data to be guaranteed to be valid because your serial clock is going to cause sampling of that data on a rising clock edge. And after the clock edge has fallen, then you can swap the data out. So you can change your data only after your serial clock line has fallen. And that kind of enables you to do what you like because nobody's going to be mucking about while the serial clock is in its quiescent state. So if I have a little code going, I can make sure I've suppressed the serial clock line and know that the devices are not talking to one another. I don't want them talking behind my back because they'll probably be talking about me or something. And they should know when they should be listening, and they should know when they should be reading information on the data line. And we don't need them to start sending information all at the same time. That's a bad idea. So you want them to act as slaves and not talk until they're addressed. If you have two devices with the same address on the same small local area network, that's a problem because they're going to start responding at the same time, and that's going to cause collisions and errors and all kinds of issues that you will find very difficult to debug just because you have two devices with the same address on the same local area network. That's not good. Okay, just kind of put that out there. I know it sounds obvious and probably it doesn't need to be said, but I got to figure somebody's going to end up doing this, and it's a bug that's going to come back and bite you later. So let's see now. What else do we have here? So we use one clock. It synchronizes all the devices. The master tells the slave when to talk and when to listen. The slave devices, well, could be anything. Other Arduinos, all kinds of interesting sensors. You could probably make an I2C interfaced servo, which might be really good if you wanted to use a 2-wire bus to connect up all the joints of your robot arm, just because it's a convenient way to go. In fact, you could probably use a metal robot arm to act. The metal could be the ground, but you're still going to need power, and you still want to have your clock and your data. So let's see, what else do we need? Oh, here's the address, 7-bit address. Gives us 127 different devices. And you can get an acknowledgement back from the slave, which is good. You want a little two-way communication going on. And that's a thing that happens in the data link layer, right? Because if you think about it, when you transmit data, if you don't know that the data has gotten to the receiver, then you're kind of just talking into the empty room. You don't know if anyone's listening. So you like to have a little acknowledgement, like, for example, received and understood, or, checksum error or parity error or something, and that will cause an automatic retransmission request, or ARQ. And so that's a standard part of most data link layer protocols. You want to have some kind of automatic retransmission request going for data link layer protocols, because that enables you to know that the data that you're sending out is actually getting there. Link access protocols, a lot of times what will happen is they'll have error correction built in. And if they find that they're getting too many negative acknowledgments, they'll be more aggressive with the error correction. They'll add some more overhead bits, or they may back off and make the packets smaller. Actually, making the packets smaller is a good technique for improving your overall throughput when you have a little bit more error. Because if the packets are smaller and you have to retransmit them, you're not retransmitting as much. So here's another example with the wire library. Here we do wire begin again. And presumably we'll get some sort of acknowledgement as we go with our transmitter data output. And this is device 20, and we're sending out some ASCII, and then we send the actual value, and then we end our transmission. And so presumably data comes in, serial clocks are handled. If there's a negative acknowledgement, it becomes a reliable means of moving data from one point to the other. You know, you can build that into the protocol for the bus. So when I begin transmissions, I want to know if I'm going to have a reliable point-to-point communication pipe. I want data to be able to go in the same order in which it comes out, and I want somehow the lower layers to take care of the error correction, the I'll call it automatic retransmission requests on demand. And you can kind of see why that's important. And you would get that from, well, from TCP/IP, right? Because TCP does a transmission control protocol on top of the routing layer, which is known as Internet Protocol. So typically you'd have physical layer, that'd be like Ethernet. Then you have your data link layer, that'd be like point-to-point protocol over Ethernet, or media access control protocol, or known as the MAC layer, or MAC sublayer, if you like. You have a routing feature, which is done in the network layer. That would be IP, or Internet Protocol. On top of that, you have a transmission control protocol, or TCP. And what that does is it controls the packets going and then stopping and waiting for an acknowledgement, or timing out if it can't get an acknowledgement, and retransmitting. So that's the automatic retransmission request. And any one of those layers can have, and often does have, some kind of error control. But error control at the bit layer is not going to be the same as error control at the TCP layer, because error control at the TCP layer assumes routing's being taken care of. And all they have to do is an automatic retransmission request and a timeout condition. So I2C, got to read the data sheet. If there's anything I can communicate with you about this course, is real engineers read the data sheets. That's what they do. That's what I do. Whenever I'm coming across a new chip, I got to read the data sheet. It'll give me the protocol. It'll tell me which bits do what, how to formulate the slave address, how to look for acknowledgements, all that good stuff. So typically, if I want to request information from a device, I need to know its address. I need to know how much data I'm expecting, but more importantly, I need to know the semantic context of the data. In other words, you know, it's sending me 32 bits. Okay, so what? What's the 32 bits for? Well, for the temperature data, it's temperature in centigrade. That's really important, right? Because if it's temperature in Fahrenheit, then I don't have to do a conversion, and the compiler doesn't know if it's Fahrenheit or if it's Celsius. It doesn't know. It couldn't know. Only somebody who reads the data sheet can know that. And so these are kind of important questions that you should be able to get from a data sheet. And master-slave correspondences also require an address, just as slave-master correspondences require an address. And there's all kinds of interesting protocols for acknowledgement and then a transmission back, right? So here what we see is we went out to the slave and we said, at this address, you know, give us a read. And so there's some data here which comes back with an acknowledgement from the slave. And that's sort of a typical sort of thing. So the wire library, this is called the two-wire interface, TWI, or the I2C interface. That's what gives us the ability to do all of this, I'll call it communication. And so the communication protocols that exist here will work on a wide variety of different machines, not just Arduino, not just Atmel devices, but Philips devices, microchip devices, all kinds of devices. And so I keep hearkening back to, you know, this one-dimensional protocol where the addresses and the meanings of the different bits are important. And you need to be able to try and read some of the data sheets in order to figure out how this stuff is going to work. So here's the basic I2C API. We can begin at an address. We can request data from an address. We can bid transmission to a specific address, end a transmission, figure out how many bytes are available, how many we received, and do things on receive and on request to act as an interrupt. So that handler might be a pointer to some sort of a method or function that you pass in. And then that's going to get invoked whenever data comes into the system. So that's kind of an interesting idea. Let's take a look at a real example here. I know some people didn't make it to the lab yesterday, so I just thought I'd play this little video here. So that's the Dallas Semiconductor 1302 with the CR2032. So this is 20 millimeters in diameter, 3.2 millimeters thick. And we had a lot of problems with these CR2032s yesterday. A lot of them were dead. These are 10-year batteries. I don't know if it's been 10 years since I got them, but maybe it has. I don't know. And then this little crystal in here, that's a 32,768 hertz crystal. That gets divided through by 2 to the 15 to give us a 1 hertz clock. And then let's see if we can see the other side of this bus. All right, this looks like power and ground over in here. And these look like non-standard connectors. Because normally I would be using 4 and 5 for my 2-wire interface. But you can reassign that to anything you like. In fact, I've got this already set up next to the computer, but no sense pointing a camera at something you can see already. That was not supposed to be a complicated lab, by the way. But for some reason, I guess because we had bad batteries, didn't work out so good. Here's a that 1 megabit ultra low power serial RAM that I was alluding to earlier. The standby current is astonishing, less than a microampere. I mean, that's, I don't know, that's nothing. So presumably you can get these things in vast quantities, like on a reel, 3,000 to a reel. And the price goes way down when you do something like that. If you buy one, it's about 85 cents. But if you're going to buy 1,000, the price goes down a lot, which is kind of cool. Let's see if I can get back to the PowerPoints. Any questions so far about the 2-wire interface or I2C? So I was thinking that maybe I would call on people because people are so quiet. August, how are you doing out there? Do you got any questions about the I2C interface? August, are you with us?
Yeah, I'm here.
Oh, okay. What do you think?
I'm okay, Professor. Thanks.
You're all right? Okay.
Yeah.
You're the first on my list here, so I guess because you begin with an A or something. So I thought I'd call on you. So let's see now. We have addresses in 7 and 8-bit versions. We can have 256 devices, I guess, if we want to push it. I'm still trying to get around the idea of having 127 devices, never mind 256 of them. I like the I2C interface because it gives you a sense of component development. Anything that you want to drop onto the interface, you just put it in your block diagram, and when you're doing system design, just keep adding things to the I2C bus. Just throw it on the bus and plug it on in. And if you know the address and you know how to write data to it and read data from it, it's just another thing on the bus. So that's a great way to do design. You don't have to worry about allocating additional pins from your Arduino. And it expands, it scales nicely. So I'll show you another example of some code where we use the request from method to get some data. So this is some double EEPROM, and this is also a sub $1 chip in unit quantity. Now it only gets you 3 bits for an address. And a lot of times things are limited in this way, but the manufacturer figured that was enough. And in some sense, one could make a compelling argument that if you needed more than, this is 32 megabits. If you needed more than that, by adding 2 to the 3 or 8 different ones, there's something going on here that you ought to think seriously about just buying a better microcontroller or something for. So here's the serial clock line. There's the serial data line. Here comes the 3 bits for address space. There's a write protect, and there's also a ground. So VCC and VSS are power and ground respectively. So let's see, we'll request 6 bytes from slave device number 2, which is going to be our little double EEPROM. We'll check to see if anything's coming in from the wire, and then we'll grab the byte and print it out. Simple. So I get 4K bytes of memory in each one of these little chips. And that, that might be good, right? Because if I have 4K bytes of memory, maybe I could use it as a digital delay line for my A-to-D converter in my DAC. And in fact, if you think about it, you could probably get an I2C DAC, use the A-to-D converter in the Arduino, add a little memory, and make a really nice delay line. Big echoes, things like that. So here's the question that you might like to ask and then answer. How do I get data from a device when I want so many bytes? A lot of times you're maximizing your data throughput when you do what's known as a blind data transfer. In other words, if I can get 1 byte at a time, that'll work, but there's so much overhead in doing it, you're better off getting 100 or 200 bytes at a time. And in that way, it makes better use of the network, the 2-wire network. And I'm going to use the term network and bus interchangeably because it truly is a network. It's just a half duplex network. Has anybody here ever heard of MIDI? MIDI is a musical digital interface which is used for synthesizers. That's a 38 kilobit per second half duplex network. And it's, or you could say simplex local area network that daisy chains. And that's from the 80s. But people used it for hooking synthesizers together with one another. It uses a funky little 5-pin DIN connector. So let's do an example. I'm going to get an example out of the Arduino here. I'm going to go to the wire interface, and here's an I2C scanner. Now I don't happen, well, actually, now that I think about it, I do have an I2C device on here. I've got an Arduino with a real-time clock. Just out of curiosity, I'm going to bring up my serial port monitor, and looks like I've got more than one device. I don't know which one is which. Oh, here we are. It's the real-time clock. So that's on 420. And yeah, it's still running. And he says it's 12:46. Oh, you know what? He doesn't know that we had to fall back an hour. I've got to reset this thing. Well, who cares? What we'll do is we'll go in to the I2C or wire library, which is down in here. We'll do a scanner, I2C scanner. I've never run this before, so this will be new. And let's see what we got here. He runs at 9600 baud. So we should go back to our monitor, change it to 9600 baud, and then proceed to upload the scanner. Let's see what happens. No I2C devices found. Well, that's not right. The real-time clock is there. And goes to show you got to test these things before you. Oh, he's doing the Leonardo. That'll do it. Maybe. I don't know. That should have worked. I would have thought. Let me try another one.
Isn't the real-time clock a 3-wire module?
Is it?
I believe so.
Let me take a look. Oh, it's not running on 4 and 5. That's the problem. I have to change the way it's hooked up, because it's hooked up to yeah, the DS 1302 has got data and clock, but he also has a reset. So if you're including the reset, yeah, that's a 3-wire. But the thing is, he's not on the standard, right? He's not hooked up to the standard wires of 4 and 5, because when you look at how that wiring was done before, we had it hooked up to the digital wires. And I'm not going to rewire it now, because that's not good. Rewire on the fly. I guess I could. Well, no, I'm not going to do that. Yeah, the DS 1302. That's this thing here. You see, he's not on lines 4 and 5. That's a problem. They won't, if he's going to scan lines 4 and 5, it's no good. So you can see what he's got here. He's got VCC ground. This here is your data. Underneath is going to be your clock, and then comes reset. So this is a 2-wire interface, but it just happened to include a reset line. You can also see that here, DS1302 data sheet. Let's see, how much are these things anyway? $3. Oh, it's an outrage. Well, it doesn't cost anywhere near that when you buy the actual board. I'm not sure why they're charging so much. Let's grab the data sheet and see what it looks like. So there you go. He's got one I/O line. He's got a serial clock line. Now this chip enable, I think you can just wire that so it's always enabled. I don't think you have to use it. Let's see what else we got. Yeah, so it's I/O, serial clock, and then the chip enable, if you want, you can just leave it enabled. You can pull that to 5 volts. Although on the board that we have, I think it was labeled reset. Not quite sure why. This chip does not have a reset. Maybe it lost something in translation. So here's another diagram of the data going out to the I2C device. This one's a double EEPROM. Uses a slave address and some bytes where the address might begin, and then a series of data bytes. That's part of the overhead, right? So the start bits, the stop bits, the address bits, the slave address, that's all part of the overhead. So it makes sense if you're doing a blind data transfer to make the number of data bytes rather long, especially if you can transfer them reliably. Here's an I2C interfaced LED from Blink M. I'm not sure. I never know quite why people do the things that they do. Maybe this is good for educators. But it's got 2 lines, data and clock, and then of course it needs power and ground. Here's the EEPROM again, and now we're going to once again outline why we would like to transfer more than 1 byte at a time, because you have the overhead of a start bit, a stop bit, an address for the slave, a byte address for the data, and then you should probably get a whole block of data at once. You don't want to kind of waste the bandwidth on that one. So blind data transfers, that's kind of a big win for this device. And that's what I have for you for I2C. So I thought that was educational. Now, from the point of view of rewiring things, I could almost see trying it. So what I'll do is I'll take the, go back to the first slide. Somewhere in here, we say what the standard is for data line 4 and data line 5 on the Arduino Unos. And so what you want to do is try and come up with something consistent with that. So here it is. Serial data is line 4. The serial clock is line 5. And so I've got my brown wire on the serial clock. And so that has to go out to line 5. So my data line is a black wire that goes to line 4. So now I've got it hooked up. Now the big question is, what happened on the monitor? The answer is, I don't know. I have to look. Nothing found. Oh, it's very sad. Here, let's reset this thing. Nope, it's not working. Well, I'd be worried if it worked the first time anyway. I probably wonder if it's burning up now. Last time I tried one of these things and the thing got so hot I burnt my finger. So it was a wiring error on my part, and I probably shouldn't be doing these things while I'm trying to chit chat with the class. So there's one other thing I wanted to kind of discuss with you guys, and this has to do with programming. And I think programming is an area where, I don't know, maybe some of you feel a little intimidated. And so what I thought I would do is come up with an interesting couple of Tinkercad examples where you could see how classes work with Arduinos. And so what I'm going to do here is this is a simple blinky light example, but I wanted to give you an introduction to classes. Now, you guys have probably seen classes before because you've seen Java, so you kind of know what classes are. This is just like it, with slightly different syntactic flavor. So here's class Flasher, and it's got an LED pin associated with it. So the flasher refers to an LED. He has to have a time when he goes on and a time when he goes off. And you can have one of those for each LED, and you can make an instance of an LED, each knowing his pin number, his on time, and his off time. And then his state, whether or not he's on or off. And if we have the previous number in milliseconds, we should be able to determine if it's been on for too long, or if it's time to turn it off, or if it's been off for too long. So when I make a new instance of a flasher LED, I spec it by the pin number that it's associated with, the number of seconds it should be on in milliseconds, the number of seconds it should be off. And then I can specify the pin. I can specify the pin mode, right? That's since I've got an LED on the output, I have to make sure that the digital output pin is set up for output. The on time and the off time. This is something I have to record. And my present state, which I'll start off as low, which means off. In previous milliseconds, we'll start off as 0. And we'll make this whole constructor, which returns nothing, not even void, public. That way I can make new instances of these things. What I'll do is I'll call update in a loop. And what I'll do there is I'll get the current time in milliseconds. And if it's high, then what we'll do is we'll figure out how much time it's been on. And if it's beyond the state it's supposed to be on, then we'll turn it off. And then we'll take a snapshot of the current time in milliseconds and update the LED to the correct state. Otherwise, if it's low, we'll look at the off time versus the amount of elapsed time. So this is going to be what we call elapsed time. And in fact, what you could do if you really wanted to refactor this properly is you would write a long for elapsed time and set it equal to that difference right in there. And then use elapsed time and see if that's longer than the amount of time it should stay on. And if it is, you can turn it off. Now it makes a little bit more sense. We'll do the same thing. If it's low, we'll check the elapsed time. And if that's greater than the amount of time it should be off, then we'll turn it on and we'll write that state out to that particular pin number. And that is an instance, well, let's say it's a class about which you can make an instance, and it ends with a semicolon. So that semicolon in there is the end of the flasher class. Ends right there. And it has to end with a semicolon. So now I can make a new instance of an LED, and he's on pin 13. He stays on for 500 milliseconds. He stays off for 500 milliseconds. He's got a 50% duty cycle. And then we do the same thing for pin 12, and then do the same thing for pin 8. But in fact, the difference is we change the amount of time that it's on or off. And in fact, if you think about it, when 5 times 3, which is 15, times 2, which is 30, so every 3 seconds, all 3 LEDs should be on. And so then in our loop, we just call LED 1, 2, and 3 update, 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 and they all know when to turn each other on and off. And this makes the code a lot more elegant. And you can use this for as many LEDs as you like. So now when we run the code, you can see that there's a time when all 3 LEDs are on, and there they are. And so then that's kind of a neat way to look at it. And that kind of gives you some insight into, how to do the class things. And some of you will be working on trying to create a library. And one of the things about libraries is they're based in classes. So the first thing you'll do is you'll set up a sketch with a class, just like I've done here. And then you're going to want to create a header file, move it into the library section, and have it compiled separately during the process of validation. And that'll give you a library upon which you can do includes and proceed to build up your own sort of interesting libraries for doing things. 1202. I have another example up my sleeve. Any questions about this? Chris, you're next up on my list here. You still with us, Chris?
Yeah, what's up?
So did you have any questions about creating classes in
No,
Arduino?
I actually have a little bit of experience with class coding.
Good.
Not a
good.
ton though.
Cool. So, I mean, I wanted to do a little bit of programming here just because I know sometimes people have questions about it, especially because it's not the same as Java. It's just a little bit different. But it's, it's a class. And in fact, Java is based in classes that was based on C++. So it should look very familiar to you. Let's do another one. This one I happen to like.
And classes are particularly useful with structures, are they not?
Yep. Well, each class has its own structure. So that's very good. That's true. So if you want to make instances of something that controls a stepper motor, that is a really good thing to have. And in fact, if you think about it, every robot is going to have multiple stepper motors. Every 3D printer will have multiple stepper motors. So that's that's kind of a big win. The question of why this isn't loading is another matter. Sometimes it just needs, oh, look, it's got the spinning beach ball of death. So that's good. Whoa, what happened? I clicked reload. My bad. Okay. So now we can get to the code. So here's a class stepper motor, and it's got 4 pins. And we can define how many steps per revolution are in each motor and how fast it's going to turn. And we can do the quarter stepping or eighth stepping for low torque or high torque. We can put in a case statement for the mode, which will determine whether we're in high torque or low torque, 4 or 8. And in this case statement over in here, after we've established the outputs as being, pins 1, 2, 3, and 4, whichever ones we like, we can then proceed to determine what the binary should look like. This is done in decimal. If I wanted to, I could probably rewrite this as something like, I don't know, B 1 0 0 0, something like that. And then this would be B 0 1 0 0. And then this might be B 0 0 1 0. And then this would be something like B 0 0, whoops, 0 1. So you could rewrite this in binary, but it's just done in decimal. And so then now I've got some things where I get to set the pins, because I could have multiple stepper motors. Why not? And then I have to set the mode, low or high torque, and whether or not we want to go clockwise or counterclockwise, and how many revolutions per minute we get. And then we can just call next step and determine how many steps it needs to turn. And here comes the setup, and this is cool, because now I can have the stepper motor at any given pins. I can change the number of steps in the motor, and I can set the mode. And then I can just loop the motor around and have multiple motors and control those motors individually as though they were different instances of classes, which is in fact what they are. So that's cool. This should have run, I think. And it should give us the, yeah, this is what the stimulus to the servo would look like if it were running. I could change the pattern by changing the mode. So presumably I could stop the simulation here, change the pattern from 8 to 4, start the simulation again. And because of the case statement, it should give us a new pattern for sequencing into the stepper motor. So you can see there's a lot of power here in using classes. And if you ever get to the point where you want to get somebody else's library into Tinkercad, you can take the .c file and the .h files and expand them directly into the sketch. So if you found a library that wasn't here in Tinkercad, you could always expand it into the sketch. And you can find the libraries with relative ease. So for example, here's the I2C scanner. That sounds like a good thing to have. You might like the wire.h library. So what you can do is go to the sketch folder and then take a quick look around in the super folder. Here's more examples. And then somewhere in here under source, you'll find .h and .cpp. And look, there's even a utility in here, and it's a 2-wire interface. So we should be able to open that up and take a look at what the 2-wire interface looks like. The header file will be a description of all the classes and their signatures. So all of these headers could be expanded into the into Tinkercad, and then you'd have a 2-wire interface subroutine library, which might be good if you were trying to simulate 2-wire interface devices. So here's the deal. It's under the libraries, right? So if you're going to put in something like a new library of your own, you'd want to put it under the libraries directory, and then you'd want to validate it by clicking on the checkbox, and that would go in and compile your C code against your header file and allow you to include both the header file /C code libraries and any examples you have in the examples directory. So that's a feature if you want to start writing your own libraries. So that's what I have for you for today. Hope you liked my little lecture there. Are there any questions? You've got a homework due tonight, right? Are we all set for that homework tonight? I think last time we kind of covered it pretty thoroughly. So that was good. I'm glad we had a chance to chat about it. The next time, what we're going to do is we're going to have a lab. Well, that'll be next Wednesday on the RF based well, it's called the NRF 24L01, and you can read about it actually. NRF 24L01. Here they are. They're very inexpensive transceivers, although for some reason Amazon is selling them for $18, which is insane. So here's a, I don't know what this is. Anti-interference LT. I don't know what this is. I have to look this up. The Ultra NRF 24L01. I don't know why it's Ultra. Is it Ultra? Ultra must mean better, right? Like Uber or something. What is this thing? I'm always looking up data sheets because I never know what the heck. This is a different radio transceiver than the IGBT. That's insulated gate. BJT. People use those instead of MOSFETs sometimes. Let's see. What is the story with this? It doesn't look quite like an NRF 24L01 to me. This looks like a different bug, which is okay, but it's not what we'll be doing. So the NRF 24L01, NRF 24L01, I don't know why Google came up with that thing. There it is. That's a 2.4 gigahertz instrument scientific band chip. And for some reason, my browser is non-responsive. I wonder if it has something to do with Zoom. Whenever I get onto Zoom, things start kind of getting wacky. So here's an example where these transceivers are way too close, but it's convenient because they're both sort of hooked to the same breadboard. And one is going to have, well, this little thumb joystick will turn that servo, and a little button over in here will turn on that LED. So there'll be a form of two-way communication. And these things can go several hundred feet, actually a kilometer, and even with the right antenna, 16 kilometers. But with the common antenna, the rubber ducky antenna, they can go up to about 1 kilometer in open space, which is really nice. And I don't think they cost more than $1 and a fraction in unit quantities. So if you're, I don't know, a careful shopper, I think they have them on eBay. And it's the NRF 24L01. And you'll find this.
NRF uses SPI, right?
Yeah, that's an SPI.
That's what it, but
Yeah.
you know, same as I2C, except it has the chip enable and chip select, of course.
Well, it's full duplex, and it's got a clock. So this is a 4-wire interface, including chip select. Right, because it's MOSI, MISO, a serial clock, and chip select.
And
sometimes
chip enable, but that doesn't count.
And they might have a chip enable, which you can wire, and they could even have an interrupt request, so they could have a 6th line if we wanted to use it. But we're not doing a hardware interrupt request. So that's $12 for 10. So that's pretty cheap. And these are cool because these come with the rubber ducky antenna and an SMA connector, along with a low noise amplifier for reception and an amplifier for transmission. I have a few of these as well, and they have the ability to go kilometer distances without too much trouble. I haven't tested it, but I've seen the tests on YouTube and they look convincing. So they're pin for pin compatible with the versions that have the microstrip antenna. And we'll talk a little bit more about those next time. And we're also going to have a nice lab about it on Wednesday next. So enjoy the rest of the day. stay safe, and thanks for your attentions.
Thanks,
Thank you.
Professor. Have a good one.
You too. Thank you.
Thank you, Professor. Have a nice day.
You too. Thanks.